photosynthesis is in water splitting, splitting water to hydrogen and oxygen. If you calculate delta G, you'll find out for the full cycle of making the carbohydrate that the carbohydrate only stores 1% more energy than water splitting. So when you fix hydrogen with CO2 in the plant, and the plant keeps the electrons and protons separated so you don't get gaseous hydrogen, but hydrogen equivalents, when you rearrange the bonds of water to make hydrogen and oxygen, that's where all the solar energy is being stored. The hydrogen's then translated with CO2 as a hydrogen storage mechanism to make sugar. What do you guys do today? You're going to eat food, you're going to chew it, and then what's going to happen? You're going to make CO2 come back out. The carbohydrate's going to go to CO2 plus hydrogen. Hydrogen and oxygen are fed to your mitochondria, where you have cytochrome C oxidase, and you run the fuel cell reaction. So when you look at the full energy cycle, all the atoms are balancing. CO2 plus water. Water goes to hydrogen O2 with solar input. You eat the sugar, get CO2 out, breathe in the oxygen from the plant, take the hydrogen, recombine it inside you. So when you eat a green leafy vegetable, if you do the mass balance, there's only one new mass in the entire energy equation. It's the sun. So I don't know what you think you're chewing when you eat food, but you're chewing the sun, and then you're releasing it inside you. Do the mass balance. You'll see the only new mass is sunlight. So this has worked for 2.5 billion years. You guys decided to do a 150-year experiment using coal, oil, and gas. I am the ultra-conservative. I'm not a liberal. I'm conservative because I want to work and use what's worked for 2.5 billion years. And these very liberal people called oil companies, because they're doing a 150-year-old experiment. Right? So I'm the conservative in the energy argument when I say use the sun. So that's why you use things and you want to make a fuel, and that's why photosynthesis made a fuel. So let's get into now how would I duplicate photosynthesis. And what I'll do is not worry about every one of these cofactors. Each one of those occupy research groups from all over the world. I'll break photosynthesis down into a systems engineering problem. Sunlight in, I do charge separation, I move an electron one direction and a positive charge the other. So moving charges is current, no wires. Then the plant stores one electron, one hole, driven by the sun. So the sun's made a high potential current. And then it's a battery. It stores 4 charges in the oxygen evolving complex. It stores 4 electrons in the other cofactor. But then the plant says, I need more energy density. I just can't keep putting charge on cofactor sites. So then it translates the battery into the chemical reaction of water splitting. So if I wanted to duplicate this process at a systems engineering level, I need to bring light into a material that makes a wireless current, store 4 units of charge, 4 electrons and holes, and then translate that into water splitting. And I'll store 99% of the solar energy just the way sunlight works. Now, to do that, you have 2 options. For 45 years, this is the option that most of science has pursued. And what this is called is a Gerischer cell, photoelectrochemical cell. And the way this works, and this is still a large research area, sunlight comes in to the semiconductor, absorbs the light, and it does water splitting. So in the Gerischer cell, the material that's doing light absorption is also doing catalysis. That isn't how photosynthesis works. If you look at this plant, it's separated function. It does light harvesting up here. I'm not showing the light harvesting complexes. Then the sunlight comes into the membrane, which is the semiconductor in a sense, to generate the charge. And then it slaps 2 catalysts at the bookends, at the anode and cathode effectively. So the plant separates charge. these photochemical devices aren't like plants, because you're trying to make one magic material that does everything. It's hard enough to design a material that absorbs the solar spectrum, never mind trying to do the complicated 4-electron, 4-proton catalysis. And when you do that, you see things like this in the applied physics literature. If I'm going to do water splitting, it's a 1.25 volt reaction. I have to make sure the band gap of the semiconductor straddles the oxidation potential. So, for instance, this material here, silicon, it can make hydrogen, but it can't do water splitting because it doesn't have enough energy in its band gap. And so what you find is there's even a sadder story with this approach. Not only do you have to make the thing absorb light and be a catalyst, it has to have a band that straddles the water oxidation potential. What I'm about to tell you today with the artificial leaf, it's a different concept. In that, you separate function. Put the photovoltaic between two conductors, so I'm burying the junction, it's called buried junction, and then on the conducting layers, I'll put my catalyst. The beauty of this is very modular. I can design semiconductors separately from catalyst design, and then I got to put it all together. And there are new problems here because you're going to have to get charge across the interface into the catalyst, so there's a lot of interfacial charge transfer issues. But the beauty here is I can do catalyst design separate from semiconductors. The other thing is, because it's between a conducting layer, you don't have to straddle the potential. As long as you have 1.25 volts or whatever chemical reaction you're running in solution, it will automatically adjust effectively. The band gap will automatically adjust to the chemistry you're doing in solution. This actually was a concept pioneered at NREL, Art Nozick and John Turner, right? So this has been out there, but people kind of forget about it, and they were enamored with this Gerischer cell. So we return to this issue of a buried junction. Now, the hard part, if you're going to do photosynthesis, is water splitting. I'm showing some students here, and Miranda mentioned proton-coupled electron transfer. You need to be an expert in proton-coupled ET. It's a simple reason. Electrons are quantum mechanical. They spread out. Protons are classical. They don't spread out the wave function. And so electrons can go a long distance. Harry Gray, long-distance electron transfer. Protons can't. And as soon as the electron gets decoupled from the proton, you start building in a big energetic barrier. So you need to couple on the same length scale the electron to the proton to get minimal energy barriers. Water splitting is a 4-electron, 4-proton process. So that makes it hard, and you're breaking a lot of bonds. You can go on Google and get an electrolyzer, buy an electrolyzer from Google. They've been known for almost 150 years. And you'll find there's 2 flavors of electrolyzers. Electrolyzers that do this catalysis out of a glass of water. Then you need expensive materials because catalysts decompose, so you're stuck using iridium, platinum, ruthenium. And then you have expensive membranes. Alternatively, you can work in concentrated base. There in concentrated base, the catalyst exists, doesn't corrode, but then you're under harsh engineering conditions, and so you have a heavily engineered electrolyzer. The other thing is electrolyzers are EST science. They are really great at making a lot of hydrogen and oxygen per unit time. They can run over 1.5 amps per centimeter squared. The sun only comes in at 30 milliamps, so it's overkill. So we decided a few years ago, could we take the best of both worlds? Could I make a catalyst that's cheap, a cheap oxide, say, that also works in water? So we won't use expensive or critical materials, and we'll be able to work under simple engineering conditions. And if you do that analysis in your head, I'm going to have to make a catalyst that doesn't corrode. which sends you to a point to say you need to make a self-healing catalyst. So as the catalyst is working, it might break down, but we'll let it reform again. If you can do that, you could work out of a glass of water. And if I can work out of a glass of water, I don't need a heavily engineered system. I don't need a bunch of what's called balance of system. I don't need a bunch of weight. I'm headed in the right direction to be cheap and highly manufacturable. So we set out to do that. To do water splitting, that's 1.25 volts uphill. We decided that was too complicated to bite off and do this proton-coupled electron transfer and multi-electron. So what we decided to do is study the downhill reaction, the fuel cell reaction, O2 plus hydrogen to water. And what I'll tell you is 5 years of hard work. What we found, and we made things like this. These are called hangman porphyrins. So we made porphyrins that could take the electron, and then we hung the proton right above the redox platform to do a long-distance electron transfer in and out with short proton hops. And what we learned, Dirac pioneered the synthesis of this, and Bob did the electrochemistry, is that if we added 3 electrons, and we had to do it in a special way. So this is cobalt-2, it goes to cobalt-3, and it gives up 1 electron to oxygen to make superoxide. If it wasn't basic enough, or this pKa was not proper, the proton wouldn't transfer. We would add another electron and make peroxide, and that kind of shunts the system. The only way we could break the OO bond is we had to couple a proton to the transfer to the superoxide. That would then drive a 2-electron reaction. I put 3 electrons in the OO bond, and that would break the OO bond. So now you just do the microscopic reverse. If I need 3 electrons to break the OO bond, it's the 3rd hole that I have to concentrate on to make the OO bond, and I have to proton couple it. So we also use cobalt, something Harry would tell you. You don't want the oxo wall, right? So if you get too early in the periodic table, oxygen does a lot of back bonding to the metal. It makes a very strong bond. So you choose a metal over there on the periodic table because those metals have lots of electrons. They have weaker metal oxygen bonds. So from all that work, we had a rule set. Use cobalt. Of the 4 holes needed, concentrate on the 3rd hole, proton couple it, and then when you proton couple it, don't make a catalyst that's stable, and maybe a lot of you don't know this, but the photosystem 2 oxygen evolving complex, which is the machine that makes oxygen, the cofactor in the leaf, that cofactor is being broken down because oxygen is toxic to the plant. It starts to eat away the D1 protein. The D1 protein is a transmembrane protein that holds the oxygen evolving complex in place. The oxygen starts to eat away at the amino acids, the ligands, the arms that hold the catalyst together. So every 30 minutes, the plant removes the D1 protein, takes sulfate, SO4 2- from the ground, makes cysteine, rebuilds the entire D1 protein, sticks it back in, and then this thing self-assembles. So even the plant, when you look at those little green things out there, admire them. Because first, they're running a much harder reaction than you. You're using the energy. And they're fixing themselves every 30 minutes. And we're just decaying, right? So plants, they rule compared to humans. So we set out to do this. That led Matt Cannon. People always ask, why did we make this concoction? That led us to use cobalt, use phosphate, put it in solution, and we did a self-assembly process. Here's cobalt. It's just sitting in a glass of water. You come through here and you take cobalt 2+ to 3+. When it goes to cobalt 3+, in the presence of phosphate, you get this film forming on an electrode. The electrode could be electricity out of the wall or from a solar panel. And that film, as it forms, if you go further, you find this big oxidation current right here. and that current is water splitting, and you find out it's all oxygen. So here's the oxygen just flowing off the electrode. You can run it at 100 milliamps per centimeter squared. Sun's coming in at 30 milliamps, so you're plenty fast enough to keep up with the solar flux. And you find out it's 100% oxygen. Since our discovery, there's lots of different ways to do this self-assembly process. So we did electrode deposition, and it's always dangerous when you start adding names, because when I walked in the room, I saw Shannon Stahl from Wisconsin, and I realized his name isn't here. So there's lots of names that aren't here. I'm sorry about that, Shannon. I told Shannon I'd give him a shout out. You can do gas deposition, pulse laser deposition, cobalt onto silicon, and something that's become very popular, and this is only some of the names, you can just shine light on a semiconductor. You make the positive charge at the surface. If there's cobalt out there, it takes cobalt 2 to 3, and you actually, this is K.S. Choi's work at Wisconsin. You can see the catalyst forming on the zinc oxide. So there's lots of ways to do the self-assembly. How well does this catalyst work? And I just want to go through this quick little diagram because it's not something that chemists are familiar with unless you're an electrochemist. If you're using an electrode, that's your reactant. That's part of your reactants. So the holes, or the positive charge coming out of the electrode, is a reactant. If I turn the potential up, I'm going to destabilize my reactant. And this is activated complex theory, so the bigger the barrier or the slower the reaction. If I turn up the potential, I'm going to destabilize this well, and when I destabilize it, the barrier is tinier, and the reaction goes faster. So you can't talk about overpotential. How far am I beyond water splitting, 1.25 volts? You want to be near the thermodynamic potential. You also need to know how fast the reaction is going. So that's what a Tafel plot is. A Tafel plot looks at overpotential versus log of the current. How fast does the reaction go? This is a decade plot, so I increase activity by a factor of 10 as I turn up potential. And what you find about this cobalt catalyst, for a given platinum, kind of the gold standard of water splitting, at any overpotential, this cobalt catalyst, when you normalize for the surface area of the catalyst, this cobalt catalyst is 3 orders of magnitude better at doing water splitting than platinum, for one simple reason. It can handle the proton-coupled ET. I'll show you that in a minute. But you can use electrochemistry to start doing kinetic rate laws. You're stuck using electrochemistry in this field because you're running a reaction uphill. So you have to put energy into the system. You can do it with an electrode in an equilibrium sense, turning the potential up, or you do it non-equilibrium, you bring a photon in. But that's the difference than what we usually do. When you're in energy science, all your reactions from the ground state are uphill, so you have to use different methods to do chemistry. What does this thing look like? You can actually have the catalyst as it's working. Yogi, Matt, Quabana, they built an electrochemical cell, and we did this at Berkeley with Junko Yano and Vital Ramachandra. And so what we did there is we put the catalyst, we made a mylar, we took a balloon, mylar, we sputtered ITO on it, we put the catalyst, we built an electrochemical cell, and we put it at the end of the synchrotron, 2-mile synchrotron at Stanford. And then as the catalyst was working, we could do X-ray absorption. And what you find is that that layer of material that looks like it's a solid state material, it really isn't. It's a molecular material. It's an oxidic cobalt cluster. And you have, on average, it's a self-assembly process, so it's not a pure compound in size, but the maximum is 7 cobalt atoms from X-ray absorption analysis. That you have 7 cobalts, and you can see the cobalt sits in an octahedral crystal field. So it's the classic octahedron of cobalt. That thing might not look like this to you. If you're not an inorganic chemist, they look different, but they aren't. They're the same. If I take manganese, replace it with cobalt, so this is the ChemDraw picture of the oxygen evolving complex, which we now know what that looks like, right? Last